Hi, welcome back to Calculus. Today we're looking at section 6.2 in our book, and we're going to be talking about cylindrical shells. So as with section 6.1, we're going to have volumes here that are generated by rotating around a line. In this case, on this one, I have a vertical axis of rotation. We can have horizontal axes of rotation, and that's fine too. But basically, here's the idea. We have a region, and it's being rotated. And maybe, for some reason, this is a region that wouldn't work very well with discs or washers. So, for instance, in the case of this region that I have here, if I try to do discs or washers, these would need to be horizontal discs, or I'm sorry, horizontal washers, because there is a hole in the middle. They would need to be horizontal washers, but unfortunately, we would have different rules for the radius of those washers. Here we'd be using the function to our center, and here we would be using this vertical piece that helps enclose our region. So there is another way to do these, and it's called cylindrical shells. The idea is we're going to build cylinders that work their way out and fill up the entire area. So for this one, for any particular x, we'll have a cylinder that has the appropriate radius, and it has a height. And so we're looking then at having these cylinders that are all the way wrapped around, and that's what we're going to use to build our volumes. So for a cylinder, its surface area is given by 2 pi r times the h. Now, that's for a cylinder without the top and the bottom. So we're just looking at the sides of the cylinder. So 2 pi r times h. And if we want to do the volumes of revolution, well, we take an integral from a to b. Notice that that's the beginning and end points of our region that we're looking at. And then we use the 2 pi, we use the shell radius, and we use the shell height. And so if we can figure out those two things, shell radius and shell height, we can get these integrals set up. And once the integral is set up, well, as you know, integration can be lots of fun, but at least it's set up and ready to go at that point. So I'm going to go ahead and redo the board, and we'll look at an example. Okay, so here's the first problem I want to do. Have the whole thing on the board, so that's nice. I want to find the volume of the region bounded by the curve y equal to the square root of x, the x-axis, and the line x equal to 9. So be very careful drawing these regions. We're going to then rotate this around the y-axis. Be very careful drawing these regions. If you're not careful, you'll get the wrong region, which will then give you a very wrong answer. If you're really not careful, not only do you get the wrong region, you set up something that is near impossible to actually find an answer for. All right, so for this one, I have my square root curve. I know I'm going out to x equals 9 because that's that vertical line there that we're using to bound it, and then the x-axis. So I want this region here, it's underneath the square root. Be careful. Possibly we could have had a horizontal line at y equals 3, and we would have had the region up above. So be really, really careful with drawing your regions. Once you do that, you have to ask yourself, okay, how am I rotating this? In this case, we're rotating it around the y-axis. So if you want, we can kind of sketch the region on the other side to kind of help us see this rotation that is happening. So we have these we have this region is being rotated, and we have this big kind of weird donut shape. Yeah, and so that's what we're trying to find. Very importantly, since our axis of rotation is vertical, our radius is going to use x and not y. Okay, because we're going to build shells going out from this center. So you can see I have this circle here right now, and we could think of our, of these typical shells as looking like that. Right? They're just these little circles, these little cylinders that we're drawing here at each x value. So when we go to try and figure out how to set this up, For this one, my radius actually is just x. It's actually x minus 0 because the y-axis is x equal to 0. So you can see over there I have my radius, it's just x, and the height goes from the square root down to the y-axis. Again, it's really the square root of x minus 0 for that x-axis. If we went down to say -1, the height would have to be the square root of x plus 1 for one more unit down. All right, so I have my radius and I have my height, which means I can set up the volume. The volume goes from 0 to, or the integral goes from 0 to 9. No, I don't need to go all the way to -9 because the rotation is going to take care of this whole side, right? We're spinning this thing all the way around, and so all of that, this whole side is taken care of with the 2 pi and all that kind of fun stuff. All right, so we go from 0 to 9, 2 pi times the radius, which is x, times the height, which is the square root of x. I cleaned up the integral a little bit. I brought the 2 pi out, and I changed the square root to an x to the half. 1 plus a half is 3 halves, and that's where this x to the 3 halves is coming from. So then I integrate it. I add 1, which gives me 5 halves, multiply by that reciprocal. So I get 2 pi times 2/5 x to the 5 halves, evaluated at 9 and 0. And I'll let you go back and plug in the 9 and the 0 and figure out what you get, but the answer should be 972 pi over 5. And if you're watching this because you're taking one of my classes, you could turn that into a decimal. I just didn't do it. So there you go. There's our first example. I have one more that I want to look at, and then we'll be done. So hang on and let me change the board. All right, so for our next and final example, we're going to do another rotation. We want to find the volume of the solid generated by rotating the region bounded by y equals x cubed, y equals 8, and x equal to 0, about the line x equal to -2. So this one's going to have a couple of interesting little bits that we're going to have to look at. But let's dive in and let's start with the region. So, well, you can see I already attempted to draw this whole object, but the region is really this piece right here, and let's look at that. So we have the curve y equals x cubed. Now, I didn't draw the bottom half of that cubic function because I do know that I'm going between x equals 0, like x equals 0, so the y-axis is one boundary, and y equals 8 is another. So I have this region. Notice this time I'm looking at a region that's up above my curve, whereas last time we had one that was below. And that's going to lend some interesting bits to this. So then we're rotating it around the line x equals to -2. We have this solid, and it's going to have a big hole through the middle of it. Okay, so that's worth noting first. We have a massive hole right through the middle of it. All right, so when it came time to find my radius, I know I want to be using x because, again, I have this vertical line of that we're rotating around, and so I'm going to build my shelves going out. So I want to use x, but here's the thing. My radius is actually whatever x is, so my region's here between 0 and 2. My radius is actually whatever x is, plus 2 more units because we're rotating around this line over here at -2. Right, so to go from the line of rotation to wherever our cylinder is going to be 2 units and then x. So that's why I have a radius of x plus 2. Now, when I actually am building this cylinder, its height is going to go from the line at the top down to the curve. And that's why I have 8 minus x cubed. If you always take the top of your cylinder minus the bottom, you always get the height. In this case, it's 8 minus x cubed. On the last one, where we had that square root function, we went down to the x-axis, which is 0. So we could have thought of that as being the square root of x minus 0, the bottom of the cylinder. So here our height goes from the top, 8, down to the bottom, which is x cubed, 8 minus x cubed. So the only other thing that we needed was we really needed to know that point of intersection. And since 2 cubed is 8, I know that that's where my point of intersection is, because I'm trying to find where the y equals 8 and the curve intersect. So my integration is going to go from 0 to 2. This time I put the 2 pi in front, and then there's my radius, times my height again. So x plus 2 times 8 minus x cubed. I expanded that, so I just had a polynomial. It's negative x to the fourth minus 2x cubed plus 8x plus 16. And so then I integrated it, raised all the powers by 1, and divided by all those new powers. So we end up with the 2 pi still in front, negative 1/5 x to the fifth minus a half x to the fourth plus 4x squared plus 16x. We're evaluating it from 0 to 2, and if you trust me, you get 336 pi over 5. If you don't, and you probably shouldn't, go back and try it out for yourself and see if you can get that as your answer. Okay, we just have to plug in 2 for x, and then plug in 0 and do the subtraction that we do for a definite integral. So there you go. That's finding volumes by cylindrical shells. They're kind of fun. Really, the big key is to be very careful with the setup. Make sure you know what the region looks like. Spend the time to really figure out what's the radius, what's the height, and then you should be just fine. So have a wonderful day. Thanks.